Uh, Here we go. All right. So yes, welcome to today's webinar. My name is Arya Hakimian, application scientist here at C-Therm. Just going to be here to get things going. I'll be very shortly passing it off to my colleague, Alex Mann, who will be going over the bulk of today's content on thermomechanical analysis, or TMA, one of our 101 series. Before I pass it off to Alex, just wanted to give a quick introduction to C-Therm, who we are and what we do, for folks that might be new to us. C-Therm, we are really experts in thermal conductivity, leading the space in transient methods. Our purpose is to simplify thermal conductivity testing for the materials of tomorrow. So, of course, today's webinar is more focused on the TMA aspect, which we also support, but our core is centered around thermal conductivity. If thermal conductivity is also of interest to folks, just wanted to let you know about our Trident instrument. So this is a modular system which brings together 4 different methods for thermal conductivity characterization. The idea is, being more flexible, being able to pivot into a different method or sensor type based on your materials or application really gives you the most highest chance of success at getting good quality data. The idea behind Trident and really I would say say a little bit of the inspiration comes from this famous quote from Abraham Maslow: when all you have is a hammer, everything looks like a nail. So again, with Trident, gives you more of a toolbox approach to really, pivot and tackle using the most appropriate method given your specific task at hand. So again, we won't be focusing much on thermal conductivity here today, other than just a quick little intro here. I will just make reference to our method selection guide. This was recently published towards the end of last year. If you are interested in thermal conductivity and again wanting to learn a little bit more about this space, this is a great free resource to check out. Compares a lot of the let's say standard methods that exist out there in industry, as well as some of the more novel use cases and applications. So definitely feel free to check that out if thermal conductivity is also important to your research. All right, but that being said, I'll go ahead and stop sharing here at this point, and hand it over to Alex, who will be taking us through the bulk of today's content. So thank you, Alex.
Thank you for the introduction, Arya. Just gonna get right into it. So, as Arya previously mentioned, my name is Alex, and I'm going to be going over TMA 101. It's just a little bit of intro to TMA, about the instrument, the test, and what kind of data you can get from it. So, starting off, the TMA is part of a thermal analysis line, which is commonly associated with a DSC as well as the TGA or DTA. So, first off, what measures what? All these instruments are complementary to each other. So if you really want to understand your material, it's great to get a little bit of data from every single one. So starting off, our STA, which is our simultaneous thermal analysis, that is essentially combines a TGA, thermogravimetric analysis, as well as either DTA or DSC, which gives you energy. So the STA will give you mass loss and energy. So you can see here we have some triangles and some squares, or not squares, X's and some circles. Grab my laser pointer out. We can go down a little bit. So the STA, it can be good for energy events such as melting, crystallization, any phase transitions, and then anything mass related, such as dehydration, decomposition, combustion, or oxidation. Now, we do see some situational marks here, and that's just because the baseline isn't as stable than a true DSC. It's just the way that the furnace is built, and there's a lot more area in the furnace. There's not a stable floor in a TGA DSC. So that's why these are very situational. If you really need the exact energy precision for things like heat capacity, Curie point, and blast transition, then the DSC is much better for the job. This can do all of the above with the energy very well. And lastly, the TMA measures expansion. So that can be from a glass transition. It can just be regular expansion, shrinkage, sintering, It's also softening. It is a mechanical, or a physical property. And lastly, you see here for the phase transition, there is a situational. So it can do solid-solid transitions. Or if you're working with a compound such as a rubber, where there's a small percentage of it will go from liquid to solid, it can do that as well. But it's not very, useful. It's not meant to do full phase transitions such as liquid to solid or solid to gas.
Alex, sorry to interrupt there.
Yeah.
I just want to flag you're in the presenter mode, is what's being shared. Just wanted to let you fix that there.
Oh,
Sorry about
cool.
that.
Yeah, no worries. It's happened before, and I'm sure it'll happen again. I'm gonna fix that real quick. All right, is that better?
Looks good. Thank you.
Good. Thank you for that. Sorry about that, everybody. Happens to the best of us. Technology, am I right? All right, yeah. So TMA, it's good for glass transition, some phase transitions. Its main thing is expansion, but that also includes shrinking from sintering, and because it is a physical, it can also do the softening temperature. So I'm going to be going over CTE a lot, which is an acronym for coefficient of thermal expansion. I'd like to go over that real quick, just so we're on the same page. So this is just a term that we've come up with in order to describe how a material will expand or shrink over a temperature range. So the units of CTE include, micron per meter Celsius, parts per million per degree Celsius, or e to the negative 10, or sorry, e to the negative 6 per degree Celsius. I personally choose ppm per degree Celsius because the rest are a little bit of a mouthful. So whenever we do our CTE, we need a reference point because we're expanding from where? We need to define this. So as we can see here for our formula, our CTE is going to be essentially our expansion as a percent divided by the change in temperature. So on a expansion chart, it'll look like this. It's going to be slope for the rise over run. So why is CT important? Why is it, necessary? Why do people require it? Well, first off, it's always good to know how your material is going to behave over a different temperature range. You can use to get your material as a density as a function of temperature. Density is very important for any simulation, modeling, or even just calculations. Thermal expansion can lead to unwanted stress, failure or warping, delamination, things like such as that. So it's really good for determining the compatibility and limits for when you're pairing materials. So we got a little, visual down here where we have two different materials at room temperature, but then when you chill it or bring it up to temperature, we see that they're not compatible and there's some delamination and or warping. For brittle materials, you can get thermal shock, which can cause cracks or, plain old failure. So when rapidly or even unevenly heating materials that are brittle, it can cause one part to expand, which then can crack because it's very brittle. It does not want to expand much before breaking. This is very important for ceramics and glasses because they are susceptible to thermal shock. So if we lower the CT of these materials, so if they expand less, well, then there's less chance of them breaking or cracking or failing. A great example of this would be cookware. So if you have your, ceramic cookware, glass cookware inside the oven at 150 Celsius, you want to be able to take it out and let it cool on the counter at 25 degrees Celsius without getting any cracks or it shattering. Something else to think about is for continuous structures such as rails, bridges, pipelines. I mentioned that it's based on the initial length. That's how we determine CTE. So if we have these really, really long structures, they're going to expand by a lot. So sometimes you can use, you know, expansion joints or other things can be implemented in order to prevent any failures for these types of structures. There's also warping to think about. So if material expansion is restricted, or if you cool it too fast or heat it up too fast, there can be warping. So we see this in polymers, metals, woods. So we got a nice little schematic here where we have two unrestricted metals. And then when we heat it up, one expands a little bit more. However, that begs the question, if we were to restrict them, how is it going to react? Where are we going to see some warping? In this scenario, we will. Now, what if we combine a brittle material and a ductile material? great example would be vacuum tubes, light bulbs, reed switches, diodes, where we have a metal or like attached to a glass. So as I mentioned, glasses, you want to have a very low CTE. Metals will have a little bit higher. So you have to well align the two so that when you create it, when you wet the glass and you combine it to the metal, it can cool off without causing a large stress on the glass, which can result in breaking, cracking, or even failure. So let's kind of go up into the TMA instrument and kind of how to run some tests, what you need to look out for. First things first, ideal sample size is going to be between 10 to 20 millimeters. So for TMA, the larger sample gives a better resolution. So if we look at expansion as a percent, let's say our sample will expand by 1%, and your sample starts off at around 20 millimeters. That's going to be 0.02 or 2. And then if we half that and we have a 10 millimeter sample, the expansion is going to be much, much less. So we lose resolution because it's a lot easier to detect a larger expansion than it is for a smaller expansion. Something else that needs to be considered is the diameter of the sample. So if we have a sample that's too thick, we can cause a large temperature gradient within the sample. We want to avoid that. If our sample is too thin or narrow, then it has some trouble standing up on its own. And lastly, you want the top and bottom faces of the sample to be flat, flush, parallel, so that the sample isn't crooked or the rod's not going to slip or slide. So there's two kind of types of compression TMA. We have our compression, regular or non-differential, and then our differential. So the biggest thing between the two is that, one of them has two rods and the other one only has one rod. So the reason for this is that if we have a second rod, we can simultaneously run a reference sample in order to get better results. I'm going to go over that in a sec, just after we go over the rod types. So something else you might have noticed back here is that this rod is arced and this one is flat. So the reason for this is that for the arc type rod, it redirects all the force into a single point. So that way the pressure on the sample is greater. This is good for samples such as ceramics, glasses, metals, where the force isn't going to cause the sample to buckle or as it gets heated up, the sample isn't going to be soft and our rod will penetrate. We want to avoid that. So that's why we can use an arc. However, if a sample is a polymer, then as we heat it up, it runs risk of getting soft. And at what point will the polymer, its viscosity will take over and all of a sudden the rod will start to enter the sample and, give you an error. So that's why we use the flat for the polymers because it distributes the force over a larger area. So for the single rod, here's a theory a little bit. So we have our observed expansion. This is what the measurement or the instrument records or measures. And it measures expansion. It doesn't know where it's coming from. So in reality, it's going to measure the expansion of this support pipe, the sample, and the detection rod. So there will be some sort of error. However, as you may have noticed, it's made of quartz, which we see here has a very, very low CTE. So when we're measuring something like a polymer, the error caused by the detection rod and support tube is negligible because polymers can have CTEs in the order of 2, 3, 400. So if we have a little tiny bit of extra expansion, it's not going to cause that much of an error. Now, if we're measuring something such as a glass, a metal, ceramic, which has a much lower, we'll say within the range from 2 to maybe 30 ppm, well, now we're going to see quite a bit of an error due to the expansion of the setup, essentially. So the way differential theory works is that we have the coil and the core that are connected to each other. So when the reference sample pushes up on the coil, it's going to take the core with it. So the coil measures the reference, then the core measures the sample. So now our observed is going to be the core minus the coil. So because we have a negative, and each of these terms include the detection rod and support tube, whenever we expand it, we're going to be left with the observed expansion is going to be the sample minus the reference. Now, this is what we're measuring, and because it's a reference sample, we know what its expansion should be. So whenever we switch it, we can get a really accurate expansion using this differential system. Think of it as you're measuring a blank or a reference simultaneously as the sample you're measuring. Now, the big advantages of this is obviously that it's needed for non-polymers, such as glasses, metals, ceramics, things that have a medium to low CTE. It's also really necessary for TMA at the temperature extremities. So most people like to use the term coefficient of linear expansion. That's not entirely true. The material's expansion doesn't tend to be exactly linear. As it gets warmer, it tends to curve upwards. And as it gets colder and colder, it tends to curve a little bit downwards. So once we get below -40, the expansion really slows down. And even if you're doing a polymer or something, you'll get really low CTE values, which is why you need the extra accuracy of the differential method. And as well, above 1100 degrees Celsius, that's when we approach the softening temperature or the glass transition of quartz. So we can no longer use it, and we have to switch over to alumina, as you can see here. Alumina has a CTE of 5. So if you're measuring another ceramic that's within that range, you don't want the error of the holder and support tubes. That's why you need to use the differential method to cancel out the holder's expansion. And lastly, I mentioned that there is a ideal sample is about 10 to 20, but sometimes that's not always possible. So having the differential method does allow for the expansion of a low thickness or low height sample. So here's an example of the differential stage method that I just mentioned. It's used for samples that are less than 10 millimeters. So what we do is we have our reference sample, and then having another sample, or sorry, another material that is the same material as a reference sample, we call it the stage, and that's what we prop our sample on. Now, because these two are the same material, we can then cancel out the expansion of the stage because it is a reference material. We know how much it should expand. And then we can get a really accurate result for this low thickness sample. So this is great for, pellets, sheets, pills, wires, things that are just naturally small. If your sample is hard, you can't shape it, or sometimes when you're doing a synthesis of a new material, you can't really make that much. So being able to, reduce the sample size and measure these small samples is very helpful. Now, does having a smaller thickness affect the results? Ideally, as I mentioned, you do want to have a larger sample to give you a higher resolution. However, as you can see here, when you do it correctly, you still get great results. This was a copper plate that was 0.4 millimeters in thickness. And when we compare it to a literature value at 300, we can see we're pretty close. Now, because it's such a small sample, the expansion isn't as linear as we'd like it to be, but we still get a good idea, pretty close idea of what the expansion is. Something else to consider is that if we have a multi-layer sample, we can use this technique to kind of isolate one layer and get the expansion of just one layer. So we use a differential method, and we use a reference material that is identical to the substrate. And in doing so, our substrate now becomes a stage, and then we can isolate or take away the stage's expansion, and then just get the expansion of our sample. Now, one thing with this is that if you remember that larger sample gives better resolution. So if your deposited sample on a substrate is very, very small, like in the micron range, well, if we're measuring 1% of something in the micron range, we're not going to get a very big expansion, and you're not going to get very good resolution. Something else to consider is that for those who are familiar with DSC, TGA, STA, you'll realize that the TMA sample is much, much bigger. So when you're using these other methods here, you'll often use 10 to 15, 20 milligrams of sample. While in the TMA, we have this large, 20 millimeter tall, 5 millimeter thick sample. So thermal inertia can cause the sample's temperature to lag behind that of the furnace thermocouple because we're using such a big sample. So here, what you can see is that the outside of the sample can be warm, almost close or mimicking the furnace temperature, but in the inside, it can still be a little bit colder, 5, 6, 7, 8, 10 degrees Celsius behind. I like to think of it as when you're cooking something big like a turkey, you can have the outside be nice, crispy, warm, but when you stick your meat thermometer in, the inside can lag behind by 10, 15, 20 degrees Celsius. We don't want this happening inside of our TMA run, because what happens when the outside is undergoing glass transition and the inside isn't? Well, then we can get some delayed values or some weird stuff going on. So something to consider is that if possible, you can make a hollow sample just in the bottom, and then now you can actually put your thermocouple inside the sample to get the inside sample temperature. So we can see here for a quartz reference block, the inside is hollowed out. And then for this nickel reference, the inside is also hollowed out. So then, as I mentioned, you can stick the thermocouple inside the reference. So if you're unable to actually burrow into your sample, then you can use the reference sample to mimic your actual sample. If you just want it out in the open, maybe you want to represent your own, you know, process or different conditions, you can have it in the open. Or if you want material property, most accurate temperature, you can then stick your thermocouple inside the sample. So this is an example of the expansion and softening of an ABS pellet using the differential stage method. What I want you to look at here is this is the dialectrometric softening point. Eventually, the ABS pellet becomes so soft that the force applied by this rod, the rod actually begins to penetrate and enter the ABS pellet. This isn't inherently an actual event because a pellet like this won't shrink. It's just an inherent thing that the TMA records. And that's not a bad thing because you can use this diametric softening point to gauge at what temperature your samples will become soft. One issue with this is that if you go too high and your sample melts, or if you enter the sample too much, it can fuse to the support tube, it can fuse to the rod and damage your setup. So essentially what you can do is you can set a meltdown protection in the software. So here it's set to -10 microns. So we're going to measure our run. We're still going to get the softening point, but then once it reaches this -10 drop, it's going to auto stop the measurement. And then there's also the hardware version you can use where you can use anti-fusion disks or spacers. And these are just sacrificial pieces that you can put above and below the sample. So if it does melt, it'll stick to these spacers instead of the detection rod or the support tube. So because these spacers are made as the same material as our reference samples, quartz, these can be counted as a stage, and we can factor out their expansion so you can keep your really accurate results during this. Now, we can combine all the above to temperature check our TMA or our thermocouple. So what we can do is we can have the spacers, tiny little bit of reference metal, and then our stage. So we're using the differential stage and our spacers. And we can just heat it up until the reference metal melts. So because it's a crystalline, very sharp melt, this won't become soft until the actual temperature that it melts. So we can see here this was done with indium, which melts at 156.6. And we saw the big drops. This is where our rod will essentially squish the now liquid indium at around 156. So we can say that our thermocouple inside our furnace is working as planned. Now, what if you do this and you get a really bad result? Something's far off. Well, we can melt a bunch of reference metals inside our TMA to create a temperature calibration so that we can recalibrate the thermocouple so that it is once again accurate. So here are some examples of some very common reference metals: indium, tin, lead, zinc, aluminum, silver, gold. So this kind of covers the entire low to high temperature. And depending on the range you are using it, it's good to use at least 3, but the more you use, the better you get for a curve. So essentially here, our calibration factor would be how far off your thermocouple is from the literature value. And what we often see is we see an upward slope like this. And then at one point it's okay. So then using this, you can recalibrate your thermocouple to get the highest accuracy results. So something else that is often overlooked for TMA is that it can actually do thin film expansion as well. So with a thin film, we can't use our typical compression because the foil or film is going to buckle. So what we have to do is now do tensile loading. So we get a new detection rod, but this one has a little clip on it, and it pulls the sample upwards in tension. So this is good for polymer films, metallic foils, fibers, fabrics, wires. The thickness is around 10 to 300 microns. And the lower limit is kind of sample dependent. If we have a very, very weak sample that can't withstand the clamping force, then sometimes 10 microns doesn't work. Or if we have a really, really slippery sample, like Teflon or something, well, then it might slip out of the clamps the thinner you go. So again, the lower limit is a little bit material dependent. Something you also may notice is that we have clamps that we need to strung our sample in. So here we have our footer, which kind of pinches the sample to the bottom of the support tube. We have the sample itself. We have our detection rod, which pulls the sample up at a force of around 1 to 1,000 microns, and that's millinewtons. It's not millinewtons. And then we have our sample clamps. So a thin film mounting jig is used to get the sample inside the clamps. So as you can see here, when you're measuring 15 millimeters, you got to have a little bit bigger sample because the clamps will take some of it. And essentially, you would insert your lower bracket and your spacer. Next, you'd put your sample in. Then you put your top on, and you clamp it shut. Now, the reason we have to use this, fairly complicated jig and mounting setup is that it's very well, very well machined to be precise, so that whenever you clamp it, it's not going to be crooked. It's going to get the exact right length every single time. Just things that help increase the reproducibility and accuracy of the TMA. Next, we'll go over some data analysis. You have your chart. What do you do with it? First is a glass transition. This is shown as essentially two straight lines that curve from one to another. So you will have the glassy region, which has a lower rate of expansion, and the rubbery region. So here, if we look at the derivative of TMA, so the rate of expansion, we'll see this is a straight line. So it has a relatively constant derivative or slope. As we transition to our rubbery region, the derivative changes till eventually it flattens out again. So using this derivative TMA, we can determine that the transition region falls within here. So around 140 to about 165-ish. Another way, a more common to determine glass transition using a point-based method is the tangential method. So we have our first line, we take the tangent of it, and we extend it. When we take our second line, we take the tangent of it, and we extend it. And then where these two slopes or tangential lines cross, we say that as our glass transition point. This one helps us with the range. This one helps us to get the exact point. Now, something to consider for materials is always thermal history and anisotropy. So this was a O-ring that was cut into a little end, a cylinder, if you would. You notice that in each direction, there's a different expansion and different glass transition. So the first heating in the X direction, we see we had a little, arbitrary little curve going on here. That is due to the thermal history from, its manufacturing process. Then if we do a second heat, you can see it is now straightened out and our glass transition has shifted a little bit. So when you're working with polymers and sometimes even metals, it's always good to have some sort of, process where you heat it up slowly and then slowly bring it back down to temperature to get the most accurate and repeatable results. And this is very important with polymers. It's a recommendation. Something else we can do is ceramic sintering. So essentially, when we sinter a ceramic, we get a bunch of small particles. We bind them together using some sort of binder, and we press it into a pellet or a rod or whatever we need to measure. And then as we heat it up, we first get binder burn off. So our binder that holds it together goes away. And then as we reach really high temperatures, the particles begin to sinter and stick together. So using a TMA, you'd want your alumina, because of course we're reaching a high temperature, and you'd want your discs. So your anti-fusion discs to prevent the sintering to kind of stick your sample to your detection rod or your support tube. So now from this, we can get the sintering temperature, so the onset where our sintering will begin. And lastly, how much our sample is going to shrink after it's fully done. Lastly, we're looking at some solid-solid phase transitions. So as material undergoes, from one state to another, such as for this example, from its martensite to its austenite, we can often see a shrinkage because as the molecules or the atoms align into a more comfortable state, they give some shrinkage. So for something here, we can see that in the martensite, we have one expansion or one CTE, and we undergo our transition. We have our start, we have our end, and then after, when it's in its new state, there's a new slope. So there's a new rate of expansion. So that's something else we can do. I just want to say thank you for coming to my presentation. I hope you learned something new. I believe we have some time set aside for some questions, and we do have a TMA in-house. So if there's any need for lab testing, you can reach out, and we'll be sure to help you as best we can. Thank you.
Alrighty, thanks, Alex. So folks, yeah, just before we get to the Q&A, I see there are a few questions in the chat. Just going to run through a little bit of an outro here to wrap things up. So, if you were looking for maybe more content in the same vein, please check out our website, ctherm.com. Lots of past webinars, tech libraries with lots of good resources spread throughout. Definitely a good place to check out if you're kind of interested in this type of material testing and application space. I wanted to just make note of a couple upcoming webinars that we currently have scheduled. I'll be doing a geological and geothermal focused webinar on May 14th. That'll be centered around our core Trident platform for thermal conductivity. And then later in the summer, June 11th, my colleague Atoshi will be joining to do a STA 101 series similar to what Alex had just done here for the TMA. As was mentioned, also, we do have a lab testing services as well as information on the partners that we represent, Rigaku and Metrovib. If you are interested in getting information on any of these techniques, any of these instruments, or our services, again, please check those out, or you can drop us a message in the chat and someone will follow up with you accordingly. If you'd like to learn more, maybe do a little bit more of a one-on-one discussion with us, where we can maybe have some time, talk through your application and really understand what the best options would be. We do offer these free technical consultations. We can do this for both instrument inquiries as well as folks that are looking at the testing services. Either scenario, we're happy to jump on and learn a little bit about what you're doing and find you the best solution. But that being said, if you like what you see and you're just looking for some budgetary information for any of the products or services, we can also provide you a quote that is, again, free of charge. And lastly, for the folks that are here from our academic institutions, wanted to make note of our academic support program. If you are looking at the instrumentation, and again, you are at an enrolled accredited university, please feel free to make note of that in your outreach. We do have a nice program here for not only a discount on the instrument, but also a few nice additional benefits as well. So just wrapping things up, give us a follow if you're not already doing so. LinkedIn is where we typically post all the upcoming events, webinars, applications, but also our YouTube channel where we put out different types of application and educational videos. So definitely give those a check if you haven't already done so. And lastly, from my side, thank you everyone for being with us here today. At this point, we're going to go ahead and transition into the Q&A session. So for folks that are dropping off, once again, thank you for joining. And again, if you are interested in sticking around, we'll be going into the Q&A right now.